Hello, I'm Anna Mackay and we're looking at sample proportions. So let's think about what we know. If statisticians are called upon to make decisions about proportions, for example, will the proportion of people who voted Liberal in the last federal election change for the next one? Or the proportion of people smoking? Or has a new medical drug increased the proportion of people cured? How would you be able to solve that definitively? You would have to survey everybody involved, a complete census. That's not always possible. So what options have you got available to you if you can't do that? You have to take a sample and look at the proportion of people that perhaps would vote Liberal in this case, and use that to extrapolate or to make an educated guess about therefore what the true population proportion might vote, and hence why this topic is called sample proportions. So for example, if you wanted to know how many might vote Liberal or Labor, you perhaps might take a sample of size 100, and if you got 42 out of that, you could say that's your proportion. And what symbol do we use for that? It's actually p hat, and we call that a hat. That's implying that it's the sample proportion as opposed to the population. This is a bit like your X bar, which is a sample mean, versus P for the population and mu for a population, depending if it's discrete or continuous data. Also worth noting that if this was one sample of size 100 and this was your proportion, if you did a different sample of size 100, you may get a different proportion. So we would obtain different values for P hat. Building on the work we did in Chapter 7, we were looking at discrete data there and expected values. And the formulas that we've got for that are that an expected value would be n multiplied by p. You might call that a mu if you like. And the standard deviation for that was the square root of n multiplied by p multiplied by the complement, 1 subtract p. Now, these were expected values, so you got numbers. This section is about proportions. So work with me while I do my best to explain my understanding of this section. Imagine you're rolling a die, and imagine back to what we did in Chapter 7. So your outcomes might be 1, 2, 3, 4, 5 and 6. And what was the probability of each of those? 1 on 6. How did you calculate the expected value? You took each x and multiplied it by its p-value and added them all up. And your expected value for this would have been 3.5. So that's sort of saying, on average, if you rolled a die many times, added up all the possible outcomes and divided it by how many times you did it, you would get 3.5. So that's a value. But what's your expected proportion? However, to have an expected proportion in binomial implies that you have a success and a failure. So to turn this into binomial is essentially sort of turning it into Bernoulli. We're actually only after one outcome. Let's call one of the things a success. So let's call getting a 3, for example, a success. So if 3 is a success, what's the probability distribution, I suppose, for a 3? So your options are getting a 3 or anything else. I'm going to call 3 is a success, and I'll call that 1. So 1 is a success, 0 is a fail. What is the probability of getting a 3? 1 out of 6. And what's the probability of getting anything else? 5 out of 6. So what's the expected value now? Multiply these together and add it onto this multiplied together. So our expected value here is a 6. But I guess in this case that's also a proportion, 1/6. The official formula here for sample proportions using this p hat symbol is you take the expected value that you would have in an experiment and you divide it by how many times you do it. So where ex is n multiplied by p, and you're dividing it by n, and what do you end up with there? You end up with p. So your expected proportion is actually the same as the true proportion. So in terms of rolling the die, if the expected value is 3.5, to find out the expected proportion, you would divide by how many times you conduct that experiment. I'm not totally convinced that the way I've just described that is 100% clear. It takes a while to get your head around. And I guess it's just an example of I'm still getting my head around how to explain it as clearly as possible. If you're in my class, make sure you ask me and we have a conversation about this. The standard deviation formula that we learnt in a previous chapter is this. And so if The same rule applies to the expected value, is that you divide it by n. Let's rearrange that to see what we get for the standard deviation of a proportion. I want to aim to cancel out those n's. So to do that, I need the square root over everything. If I change the denominator into n squared and the square root of that, essentially I've done nothing. But using surd laws, I can now extend that surd over the lot. And you can see that the n on the numerator and one of the n's in the denominator cancel out, and I'm left with this. And that's the formula that we're interested in for today. So that's the formula for the standard deviation of sample proportions. Summarizing that, if we have a population proportion of p and a sample of size n, the sample proportion p hat has a mean of p, so it's the same as the population, and a standard deviation of this. So that gives us confidence that if you take a sample and you're trying to use that to estimate the true population proportion, so that might be the number of voters for Labor, your sample will give you a rough estimation, and here's the standard deviation for it. Into an example, a coin is tossed and a tail appears 50% of the time. If the coin is tossed 30 times, we're asked to find the mean and standard deviation of p hat, which is the sample proportion of tails appearing. So the way you would write this out is that p, to find out the mean, is approximately equal to p hat, which is 0.5. And our n is 30. And to work out the standard deviation, another way of writing this as a subscript is the standard deviation with a subscript p hat, and substituting that into the formula, I'll substitute in my two proportions over n, the square root of all of that, and that gives us a number of 0.0913. So just practicing the skills on that one. So here we have an experiment where n is equal to 30 and our p-value is 0.5. So this is actually the equivalent of that coin that we've just tossed 30 times, and the chance of getting a tail is 0.5, 50%. So what would happen here? If you did this experiment of 30 trials many times, the outcome that would happen the most often would be that you would get 15 tails, so approximately half, and that happens at the peak there, 0.144, so 14% of the time to get 15. And as you can see for the other values, they decrease either side because they're less and less likely. So it's really unlikely that you'll get 30, 29, 28 tails out of 30 trials. What do you notice about the shape of this? It's the bell curve, so it's sort of approximately normal, and that's what we would expect to happen. So I guess that's a bit of a unique property here, connecting binomial and normal statistics. So in this example, mean you would get is 30 multiplied by that proportion, the probability of things happening, and the standard deviation is this 2.739. Now you might ask yourself, but hang on, wasn't the number we got on the previous screen much smaller than that? Yes, because if we're after a sample proportion, what we do is we've divided that number by n, by how many times that we did it. So if you get your calculators and you do 2.739 and you divide it by 30, you get that number that we were after, 0.0913. And as you can see, that was the formula for the standard deviation of a binomial distribution. Now, moving on to another example. Still building on though, the tail appears 50% of the time when a coin is tossed. If that coin is tossed 30 times, we're asked to estimate the probability that 65% of those coin tosses produce a tail. So what's the chance of that happening, that we'll get 65% of them? Well, the first question is, what is 65% of 30? Mathematically, to do that, we multiply 0.65 by 30 and we get 19.5. That's 19.5 what? Tails. That's not possible. So let's just mathematically play with that idea. Where is that on our graph? Where would 19.5 be? Well, here's 19, so 19.5 there. So what probability are we expecting? I realized that I needed to add in that at least, that was the question I actually wanted to ask, at least 65%. So that means it's this area here. What type of answer might you expect? Is that 50% of the time? No, much less. So let's calculate that and see if it matches what we're expecting. So we're in binomial, And so if we were to use our BCD function in our graphics calculators, which we'll do in a minute, it's going to ask us for a lower, an upper, an N and a P. What could each of them be? Our N would be 30 times. Our P would be the probability of getting that tail, 50%, 0.5. Our lower is, okay, we want 65% of the time. So we want, we want 19.5, and then our upper is up to the most, I guess, so you could go infinity, but we go 30. Let's see what happens if you've got your graphics calculators handy. So we're in menu 2, the distribution is binomial, BCD, and if you put in that lower of 19.5, maximum of 30, trials 30, and probability 0.5, error. The input value must be an integer. Because we're doing binomial here, we must have a whole number, a success or a fail. We can't have halfway between. So that's created a problem. So conveniently, to solve this problem, the fact that this resembles the normal distribution, that now gives us permission, instead of using BCD, binomial cumulative distribution, we can use the normal cumulative. And the requirements to be able to use that are that for sufficiently large n, where p hat will be normally distributed approximately if n multiplied by p is greater than or equal to 5, and this requirement over here. In the past, sometimes in some of the textbooks, we've had 10 here. Currently, we're going 5. Let's check that for ours. So what's our n multiplied by p? Our n was 30 trials, and our chance of having a tail is 0.5, and that gives us 15, which is greater than 5. So that now gives us permission to use the normal approximation in this case. So our probability statement would be, what is the chance that p hat is going to be greater than equal to 65% of those 30 trials will be tails. The values that we're going to put in NCD, we need a lower and upper, a standard deviation and a mean, as opposed to an N and a P. What is our lower? It's going to be 0.65. Our upper, so we don't, because we're using normal here, we don't stop at 30, we're going to go to infinity. So the way we write that is E98, which is 1 multiplied by 10 to the power of 98. Our mu, as we've discussed before, is the same as our proportion, and that is 0.5. And our standard deviation is what we calculated right at the beginning of this example, which was 0.0913. I'm going to tell you that the answer, what it is here, and we're going to go across and check, 0.0502. And what percent is that? That's about 5%. And remember from that graph, that's what we expected. We're just going to plug it in. So here we are, we're going into normal distribution this time around, not BCD, NCD. Our lower is 0.65, our upper is e to the 98. Our standard deviation, you can type it in again with the square root to be more exact if you like. And our mu is that proportion, and our answer, as we expected, was 0.0502. And that matched that area that we were after, that really small amount. So about 5% of the time you could expect that. Thank you. I hope this helped clarify sample proportions somewhat. Join me in the next video, confidence intervals for proportions. Thank you.